Hi everyone, I'm Gökcan. I was working with Şebnem. Şebnem is studying physics in Middle East Technical University. She will graduate this year. And we have studied versioning's high-dimensional probability textbook. We mostly studied some chapters of that textbook and mostly focused on concentration inequalities part. And yes, Şebnem will continue the presentation right now.
Okay, thank you. As my mentor Gökcan said, we study concentration inequalities, and he's also study in Wisconsin Madison University. He's doing his PhD there. And let me start with my overview of my presentation. First, in introduction part, I'm going to mention Markov and Chebyshev inequality. Those are the basic tail bounds, and we are going to use them in order to explain basic concentration inequalities. In this part, I'm going to explain Hofting inequality and Chernev inequality. Their summation of random variables based on Bernoulli distribution. So at the final part of my presentation, we go beyond Bernoulli distribution and talk about sub-Gaussian and sub-exponential distribution. And to bound them, we're going to use Bernstein inequality. So why concentration? When we don't have deterministic bounds, we use probabilistic bounds. And to do that, we use concentration. It is bounding the deviation of a random variable around its mean value. In here, as I said in my overview part, it is Markov inequality. It bounds the individual random variable by its first moment, which is expectation. And here I'm going to explain proof of it. We use the summation formula for this proof because we did this based on discrete random variables, but the proof for continuous random variables is essentially the same. We just need to replace some with integrals. So this is the formula of expectation. And we will split this into two pieces, depending on x greater or equal to a. As you can see here, this is the split version of this sum. And after that, we have greater or equal to symbol here. It's because by the definition of non-negativeness of probability, and also the assumption that we make x is not negative. And in this part, we insert the a instead of x because x can take at least a. And this equation becomes the equation 7. When we divide both sides of the equation, we get Markov inequality. And here we have Chebyshev inequality. This is another tail bound, and it explains the deviation of individual random variable by the second moment, which is the variation. And we can prove it by using Markov inequality. We can just say that let's change variables and say y is equal to this expression and is non-negative. By Markov inequality, we can write this expression. And after that, we can notice that y greater or equal to a square. As we define y, we can say that this one too. And we end up with equation 10. After that, we again set variables a equal to k multiplied by sigma squared. Sigma is the standard deviation. And our inequality takes this form. And if we simply doing this simplification, we're going to have Chebyshev inequality. So up to this point, we have talked about Markov and Chebyshev inequalities. They were bounding the individual random variables' tail behavior by controlling their moments. Markov was controlling the first moment and Chebyshev was controlling the second moment, which was variance. They are the most basic tail bounds, and we're going to use them to obtain concentration inequalities. I will mention them later in my presentation. And different from Markov and Chebyshev inequalities, Hofting and Chernev inequalities describe the tail behavior of summation of random variables. And Chebyshev inequality, we can say that is a simple concentration inequality because it was bound in the individual random variable of x, the deviation of its mean, but it's weak. So that's why actually we need concentration inequalities. But before going deeper to that, I want to explain strong law of large numbers. Let's say we have a kind sequence x1 and x2. They are identically independently distributed and their mean is mu. If we consider the summation of those x1 to the xn values as n goes to infinity, this average converges to mu, which is the fundamental result that justifies concentration of a sample mean around its expectation. And here we have central limit theorem. It makes us one step further closer to the concentration inequality. It explains the limiting behavior of the distribution of summation. When n goes to infinity, this distribution behaves like Gaussian distribution. We can say that. And after that, up to this point, we can say we can basically bound the tails of this summation by using Gaussian approximation by central limit theorem and Gaussian tail bounds. So you can ask why we need concentration inequalities. We need concentration inequalities because Gaussian approximation decays so slow. As you can see in this equation, the difference between z and the normal distribution is less than the order of 1 over square root of n. So it is so slow. We need something without using the central limit theorem. We need to bound the concentration of summation around mean. And this brings us to the Hofting inequality. In Hofting inequality, we consider the summation of symmetric and independent Bernoulli random variables. As you can see, this is the summation of xi's is less than or equal to this exponential. And this I represents summation of these ai's. And to get a two-sided Hofting inequality, we define an absolute value. Since it is symmetric and we define absolute value, the exponential is doubled. And here we have extended version of Hofting inequality that holds for all bounded random variables. To explain this capital Mi represents the upper bound for xi, and this Mi represents the lower bound for xi. And we see that this summation of deviation bounded by this. Since I have a limited time, I'm going to give a brief explanation of proof of Hofting inequality. We remember this expression from the left side of the basic Hofting inequality. And when we apply Markov inequality to it, we end up with this expression. And then the problem boils down to the bounding moment generating function of the expression in Hofting inequality. We can write this expression in the multiplication version because the probability of xi's are independent, and by the property of expectation, we can multiply them. And here we are comparing Taylor expansions of hyperbolic cosines and exponential. we obtain this expression, and without loss of generality, norm of AI is equal to 1, and let's bring this equation into this. To get optimal value, we say that lambda is equal to t. By replacing t and making the desired simplification, we have the proof of Hofstadter inequality. As I mentioned in my overview, the other concentration inequality that I'm going to talk about is the Chernoff. Chernoff bounds the summation of xi's by this expression. It has a similar proof like the Hofstadter inequality. By applying Markov inequality, we obtain this, and this again boils down the moment generating function of Bernoulli random variables, as you can see in this expression. Then we use this inequality to get equation 21, and after desired simplifications, we get proof of Chernoff inequality. Up to this point, we have covered Hofstadter inequality and Chernoff inequality. Those are applicable to only Bernoulli random variables, except the extended version of Hofstadter inequality. That's why we are in the need of going beyond Bernoulli distribution. Now we're going to discuss some extended and analog versions. We all remember this two-sided Hofstadter inequality, and when we want to focus just xi term, we have this expression, in which we can consider this as a property of random variables that Hofstadter inequality applies. And now we are defining the class of sub-Gaussian random variables. It's a wide class. It contains Gaussian, Bernoulli, and all-bounded distributions. As you can see here, the dotted line is a sub-Gaussian, and its tails decay faster than the Gaussian. As you can see, this is the Gaussian one. And in this picture, there's this super Gaussian T and super Gaussian 2. And you can see the wider dotted line, and its tails decay the slowest. And now we have general Hofstadter inequality for sub-Gaussian random variables. This inequality looks put together. We have our absolute value and double exponential. And this is the norm of sub-Gaussian, but it's not wide enough. So we need to give a random variable g, where gi is identically independently distributed. And when we consider square of the norm of g's, it is highly probable that it has some concentration, since it is the summation of IID random variables. As you can see here, the distribution here decays slower than the Gaussian. And this is the part we need to give a definition of sub-exponential distribution. It is the distribution class that has at least exponential decays. Since we cannot apply Hofstadter inequality here, we give Bernstein inequality. It is an analog version of Hofstadter inequality. It bounds the sub-exponential summation here by this expression. So in this figure, we can see Bernstein inequality for a sum of sub-exponential random variables. This distribution have two different regimes. In the center part, the deviations are small, so we need normal tails. On these parts, we have large deviations, so we are using exponential tails. Thank you for attention. This brings me to the end of my presentation.